Hello. In this lecture, we are going to study about isometries of surfaces and conformal maps between surfaces. First, let me begin with isometries of surfaces. Let us take two regular surfaces in R3. Let S and S tilde be two regular surfaces in R3. A diffeomorphism phi from S to S tilde is called an isometry if the differential of this phi, it preserves the inner product. Okay, so if for all p belonging to S and for all tangent vectors W1, W2, so we have the inner product of W1 and W2 is same as the inner product of d phi p of W1 and d phi p of W2. So note that, this inner product, it is in the tangent space of S, and this inner product, it is on the tangent space of S tilde at the point phi p. So this is the definition of isometry. Okay. So now if I take the first fundamental form, so IPW, so this is equal to the inner product of W with W at the point P. So this is the first fundamental form on the tangent space of S at the point P. So if I have an isometry phi, so phi isometry implies the first fundamental form IPW will be equal to I phi p differential of phi at the point P of W. So this first fundamental form, it is also preserved by the differential. Okay. So now, suppose you have a diffeomorphism where the first fundamental form is preserved. So suppose phi S to S tilde be a diffeomorphism such that IPW is equal to I phi P d phi P W. So the first fundamental form is preserved. Okay. So now note that, so if I take 2 times the inner product of W1 with W2 at the point P, so this will be equal to IP W1 plus W2 minus IP W1 minus IP W2. Okay. So this you can check. So therefore, now from this equation, what we have, inner product of W1, W2 at the point P is equal to d phi P of W1, comma, d phi P of W2. Okay, so this implies that phi is an isometry. Okay, so what we have proved is the following. A diffeomorphism phi is an isometry if and only if d phi P preserves the first fundamental form for all P belonging to S. Okay. So we have defined isometry. So now let me give some examples. So if I take translation, so this translation by vector A, it is an isometry. So this translation, it is an isometry of R2. Okay, so why this is true? So if I take the norm of TA x bar minus TA y bar, so this will be equal to norm of x bar minus y bar. So from this, you can show that this T, it is an translation is an isometry. If I take rotation, so r theta of xy is given by the following. So x cos theta minus y sin theta, comma, x sin theta plus y cos theta. So r theta, it is rotation by an angle theta about origin. So r theta is an isometry. R theta is an isometry of R2. So in fact, so if I take the sphere, let us take this unit sphere. And now let us take a rotation. About this z-axis by an angle theta. So let us again call this to be r theta. So this r theta is an isometry of S2. So why this is an isometry of S2? So this r theta, in fact, it is an isometry of R3. And if I restrict that isometry on S2, it will preserve that S2. So therefore, this r theta is an isometry of S2. And similarly, so if I take this torus, and again, if I rotate by an angle theta, so r theta is an isometry of torus. Okay. So other isometries of surface you can get by reflection also. So I'm not going to that thing. Now let me define local isometry. So let S tilde be regular surfaces in R3 and B be an open neighborhood of a point P belonging to S. A map phi from B to S tilde is said to be a local isometry at P if there exists an open neighborhood B tilde of phi P in S tilde such that phi B to B tilde is an isometry. Okay. Now, what is the definition of local isometry? If there exists a local isometry into S tilde at every point P belonging to S, so then the surface S is said to be locally isometric to S tilde. Okay. Let me give you an example of a local isometry which is not an isometry. If I take the cylinder S1 cross R, so S1 cross R, so this is a cylinder. So this is locally isometric to R2. But there does not exist any isometry from the cylinder to R2. Okay. All right. So how to show this thing? So let us take, so let U to be equal to U comma B, 0 less than U less than 2 pi, and B it belongs to R. And let us take this U tilde to be equal to, or let us take B here. B is equal to U comma B minus pi by 2 is less than U less than pi by 2. And again, this B, it belongs to R. Let sigma UB to be equal to cos U sin U B. Okay, so this cylinder, it can be covered by two surface patches. S1 cross R is equal to sigma U union sigma B. Okay, so sigma of U, it is an open subset of S1 cross R. Okay. So now, so the sigma, it is a map from U to S1 cross R. So U, it is an open set, and sigma of U, it is a proper subset of S1 cross R. So sigma cannot be, no, so sigma is not defined on the boundary. So sigma of U, it is an open subset of S1 cross R. Okay, so now, So what will be my differential of this sigma? So in order to prove that this sigma, it is an isometry. So sigma is an isometry onto its image. So in order to do that thing, so that is inner product of d sigma p w1 d sigma p w2. So this will be equal to the inner product of w1 and w2 at the point P. Yeah, so one mistake I have made here. So sigma, it is a map from this U to the cylinder. And I have taken a point P here. So I'll get a point sigma inverse P such that sigma maps sigma inverse P to P. So this point, it will be, let us take it to be Q. So Q is equal to sigma inverse P. Okay, so I want to prove this thing. And in order to prove this thing, if I show that d sigma, it preserves the first fundamental form, then we will be done. So in order to show this thing, so we'll show that this d sigma p preserves first fundamental form. Okay. All right. Okay. Now let us uh, compute this first fundamental form. So in order to compute this thing, so let us take sigma u. So sigma u, it will be equal to minus sign u cos u comma 0, and sigma b, it will be equal to 0, 0, 1. And the first fundamental form on the cylinder is E du square plus twice F du dB G dV square. So E is equal to the inner product of sigma u with sigma u, which is equal to 1. F is the inner product of sigma u with sigma b, it is equal to 0. And G, it is the inner product of sigma b with sigma b. So this is equal to 1. So this is equal to du square plus dv square. Okay. So therefore, so this du square plus dv square is the first fundamental form on the cylinder. Also, du square plus dv square is the first fundamental form on u. Okay. So therefore, d sigma p preserves the first fundamental form. So this shows that sigma is an isometry onto its image. Okay, so sigma, it is defined on an open subset of R2. Okay, and sigma, it is not defined on whole of R2. Similarly, sigma is an isometry on this V. Okay. So therefore, this S1 cross R is locally isometric to R2. So we got an open subset U of R2 and a map sigma such that sigma is an isometry from U to sigma U. Okay, all right. And R2 is not isometric to cylinder. So in fact, R2 is not homeomorphic to cylinder. So this fact, it comes from algebraic topology. R2 is simply connected, whereas the cylinder is not simply connected. The fundamental group of R2 is trivial and fundamental group of S1 cross R is Z. Okay. If two topological spaces are homeomorphic to each other, then their fundamental groups are isomorphic. But it is not so here. So therefore, R2 is not homeomorphic to S1 cross R. Okay. Now next, let me define conformal maps. A diffeomorphism phi from S to S tilde is called a conformal map if for all P belonging to S and W1, W2 belonging to the tangent space of S, we have the inner product of d phi P W1 and d phi P W2. So this is equal to lambda P B1 B2. So this inner product at the point P, where this lambda is a nowhere 0, or let me take it, is a positive differentiable function on S. Okay, so that is lambda q is always greater than 0 for all q belonging to S, and lambda is differentiable. Okay. Yeah, if a diffeomorphism satisfy this property, then we say that diffeomorphism to be a conformal map. The surfaces S and S tilde are said to be conformal to each other if there exists a conformal map phi from S to S tilde. Okay, so next we'll show that this conformal map, it preserves angles. Okay, so let phi S to S tilde be a conformal map. And let us take a point P belonging to S. So P is an arbitrary point in S. I have this surface and I have this point P and I have this tangent space and I have this map phi, which is conformal from S to S tilde, and this is my tangent space T phi P S tilde. Okay. Now we have two tangent vectors. So corresponding to this two tangent vectors, I'll have curves like this. Okay, so let us call this to be my alpha 1 prime 0 and this to be my alpha 2 prime 0, and this is my point P. So let alpha 1 prime 0 be two tangent vectors at the point P. Okay. So now what will be the angle? So angle between these two tangent vectors is theta equal to cos inverse inner product of alpha 1 prime 0 with alpha 2 prime 0 divided by norm of alpha 1 prime 0 times norm of alpha 2 prime 0. Okay. So now you know that this d phi, it is conformal. So this will be equal to cos inverse yeah. So let us go back to this definition of conformal map. So from this equation start, so what we'll get? So this will be equal to lambda uh, yeah. Okay, so this will be equal to 1 by lambda times d alpha 1 prime 0. Sorry, so this will be equal to d phi at the point P of alpha 1 prime 0, comma d phi P alpha 2 prime 0. So we'll get this thing from here. And this whole thing will be divided by 1 by root over lambda times norm of d phi p alpha 1 prime 0 times 1 by root over lambda multiplied by norm of d phi p alpha 2 prime 0. Okay. So therefore, this theta will be equal to cos inverse d phi p alpha 1 prime 0 cos inverse of inner product of d phi p alpha 1 prime 0 and d phi p alpha 2 prime 0 divided by norm of d phi p alpha 1 prime 0 multiplied by norm of d phi p alpha 2 prime 0. So this is the angle between the tangent vectors d phi p alpha 1 prime 0 and d phi p alpha 2 prime 0. Okay. So this shows that phi, or let me write d phi p preserves angles. Okay. So conformal maps will preserve angle. Example, if I take the stereographic projection of this S2 minus this north pole 0, 0, 1. So stereographic projection of this S2 minus this to R2 is a conformal map. And the stereographic projection, it is also not an isometric. It is a conformal map, but it is not an isometric. Okay. So again, note that, so this sphere, unit sphere S2, it is not conformal to R2. If I delete the point 0, 0, 1 from S2, so then it is conformal to R2. So therefore, the sphere, it is locally conformal to R2. Okay, let me just define locally conformal map. So similar to local isometry, I have local conformal map. A map phi B2 S tilde where S tilde are regular surfaces in R3. So a map phi B2 S tilde of an open neighborhood of P belonging to S is called a local conformal map at P. So if there exists an open neighborhood P tilde of phi P such that phi from B to B tilde is a conformal map. Okay. If for each P belonging to S, there exists a local conformal map at P, so then the surface S is said to be locally conformal to S tilde. So there is an important theorem by Burrs. So it says that if I take any two regular surface, they are locally conformal to each other. Any two regular surfaces are locally conformal to each other. Okay, so I'll stop here today.